Hello, good morning, good afternoon, good evening, whenever you happen to be watching this video. Tanya Laird here, and welcome to part 1 of lecture 7 of ENGR 231 Engineering Statics. In this part of the lecture, we are going to be exploring some of the theory of rigid body equilibria. We're going to look at the equations that are built into rigid body equilibrium, and also I want to explore the assumption, or deeply explore the assumption of rigid bodies. So this video is going to be titled Rigid Body Equilibrium, but I want to actually deeply explore the real core of the rigid body assumption and what that means and why that in particular is important. So let's look at rigid body equilibrium. Now I'm tripping over myself deciding whether to call this rigid body equilibrium or rigid body equilibria, but that really only depends on whether you're talking about the singular or the plural. But anyway, let us say we have our generic rigid body that we've worked with before. Just our nice generic potato body here, with a certain center of mass, or centroid here. And then we have a variety of forces applied to this. Let's say you have an F1, an F2, an F3, and an F4. And really it doesn't matter the exact number. All I'm trying to show is that there are a variety of forces applied to this. So we have a generic rigid body, and what that means is a rigid body of some indeterminate shape, and there are a variety of forces applied to this. Now, if this were a point particle, if this were a point particle, so let me call this a rigid body. If this were a point particle, and again, as we remember from earlier in the course, a point particle is one where we can approximate all of the mass as being located at a single point or a single location. So if we were to draw an equivalent system here, I can show an F1, an F2, maybe an F3, and an F4. And I'll forego the vector signs for now, but of course these would all be vectors rather than just scalars. So if I were to do this properly, I'd put a little vector sign over all these. Now let's talk about equations of equilibrium. What we've looked at previously in terms of equilibria of objects, or equilibrium for objects, for point particles we've discussed really just those that have only translational equilibrium to worry about. And the three equations of translational equilibrium are just ones that come straight out of Newton's second law. Sum of forces in the x direction is equal to 0, sum of forces in the y direction are equal to 0, and summation of forces in the z direction is equal to 0. Summation of forces in the x, y, and z direction, all of these must be equal to 0 in order for a point particle to be in equilibrium. And that's good enough for a point particle, but again, the defining feature for a point particle is that it has no dimensions. As we remember from our earliest lectures in this course, the defining feature of a point particle is that it has no rotation. No rotation present. Thus, we are only concerned with translation. Or I should probably say no rotation is present because dimensions are 0. If you have no dimensions, you have no moment arms. Therefore, you can have rotation. You cannot have rotation. So because dimensions are 0, no rotations are present. Therefore, must only worry about translation. You only have to worry about translation. In this context, that means translational equilibrium. So, if we have a point particle, if we can ignore the actual distribution of mass and area and etc. in an object, then all that matters is the actual forces applied to it. It doesn't matter where they are applied on that body. All that matters is just what forces are applied to it. If the dimensions are irrelevant, then I don't care where they're applied, because we're approximating all dimensions as being 0. Now, what about for a rigid body? Now, for a rigid body, this is a little bit different. For a rigid body, we are saying that the dimensions actually are important. We're concerned with, for whatever reason, we're concerned with how it rotates. Or in statics class, we are concerned with how the distribution or the dimensions of the object affect the distribution of forces. So here, if we have to worry about rotation, then we have to use 6 different equations of equilibrium for a 3-dimensional object, and these are as follows. First, we have the same 3 identical translational equations that we had for the point particle. These are the summation of forces in the x direction is equal to 0, the summation of forces in the y direction is equal to 0, and the summation of forces in the z direction is equal to 0. And again, these are the equations of translational equilibrium. But because we are also concerned about the rotational equilibrium, we have to be concerned with 3 moment equations. And these are summation of moments about the x direction is equal to 0, summation of moments about the y direction is equal to 0, and summation of moments about the z direction is equal to 0. However, I should note, well, before I get to that, I should say that these are the, well, actually I can go ahead and say, these are the generic equations. These describe the full equations of equilibrium for a, well, basically any object in 3-dimensional space, the kind of space we inhabit. If we have, sure, if you talk about like mathematically possible, not really physically meaningful, 4 or 5 or more dimensional space, you can describe it mathematically, but it doesn't really have any meaning in terms of actual engineering. We're not, we're in this class and in all engineering classes, we are not mathematicians. Like mathematically, you can describe universes that have 4 and 5 and 6 dimensions, but we're not really concerned about that as civil and mechanical and etc. engineers. We are confining ourselves to 3 dimensions. And these are the 6 equations you need for static equilibrium for a 6-dimensional or for a 3-dimensional space. Sorry. So if you want an object that actually has meaningful dimensions, if you want that to be in equilibrium, to be static, it must satisfy these 6 equations of static equilibrium. It must have translational equilibrium in 3 dimensions, and it must also have rotational equilibrium about 3 different axes. And that is, and again, that is for the full, the entirety, the maximum. This is sort of the max general case. This is the general case. This is a general 3-dimensional case. This is static equilibrium if you have to worry about x, y, and z translation and x, y, and z rotation. And in terms of what that means, if you're having trouble visualizing this, so you have your x, y, and z axis. Got that a little out of whack there. So if you have your x, y, and z axis, well, translation along the x, y, and z axis is fairly simple to imagine. If you translate in the x direction, that's just moving in the x direction. If you translate in the y direction, that's translating in the y direction. If you translate in the z direction, that's just translating or moving in the z direction. Fairly simple. But if you're talking about rotation in the x, y, and z direction, or in the x, y, or z direction, that's where things get a little bit trickier. You have to worry about rotation about these axes. So rotation about the x-axis means if you have a rigid body, it is spinning about this axis. If you have a rotation about the y, you have rotation or spinning about this y-axis. If you have rotation about the z, you have spinning about this z-axis. So we see here that if we when we go from a 2-dimensional problem to a 3-dimensional problem, things actually get a lot more complicated than it would seem. We don't just add 2 additional equations because we have the 2 additional dimensions. We actually add, well, if you look at it, we actually add three, we double the amount of equations we need. Because in the two-dimensional case, let's look at the two-dimensional case next. Two-dimensional rigid body equilibrium. If you have two-dimensional rigid body equilibrium, first of all, you don't have to worry about the translation in the z. That's fairly obvious. So if your xy, so you have your xy axis. So you have the x-axis and the y-axis. I have to draw this in a different color. Maybe I'll just go ahead and draw this in maroon. Recall my old A&M days. Oh, maybe with a not a rigid body, but a center of mass here, like so. So if this thing is to be in equilibrium about the if this is a, let's just say this maroon drawing here, this is a generic rigid body, but it is confined to the x and y axis. It is truly a two-dimensional object. So it has like, oh, I don't know, zero dimensions in the x, or sorry, zero dimensions in the z. It has dimensions in the x and the y, but its thickness in the z is 0 or negligible. Well, let's look at this. If this thing were to be in equilibrium, let's see, but if I were to have a variety of forces applied to this, let's say I have F1, F2, F3, etc. Well, obviously I need translational equilibrium. So summation of force in the x direction must equal 0, and summation of forces in the y direction must equal 0. That's fairly straightforward. And of course, because I'm dealing with a 2D system, I don't need to worry about a sum of forces in the z direction. This is a two-dimensional body, so I don't have to worry about that. However, to be in equilibrium for moments, though, for rotation, I actually only have to worry about one direction, and that's moments about z. Okay, so if you think about the right-hand rule, if you imagine a right-hand rule, like imagine taking a, okay, so take your hand and curl it so that your, so curl your fingers into like a circle, and then point your finger, your thumb in a straight line. Curl your fingers, your forefingers, in a circle, and point your thumb in a straight line. That defines right-hand rule for moments in two dimensions. So if you place that on the 2D plane, for any given force, no matter what the direction, you can see that the moment vector for any force on the 2D plane is going to be directed either into or out of the page, depending on what direction is going with whatever point you're taking moments about. So if you have a 2D problem, the moments generated by any force are going to be generated or going to be pointing either into the page or out of the page. Now, usually when we're dealing with a 2D problem, we don't actually use the z subscript. Usually I tend to write this as just sum of moments counterclockwise positive. Summation of those is equal to 0 for a 2D system. But technically speaking, if I'm talking about 2D moments, the moments are actually in the z-axis, but for a 2D system, it kind of is unstated that the moments are in the z-axis. But really, these are our key equations of equilibrium. For our 2D system, we just have sum of forces in the x direction is equal to 0, summation of forces in the y direction is equal to 0, and just a single summation of moments is equal to 0. And then the 3D, for the rare times we actually deal with a full 3D summation of moments, or full 3D rigid body equilibria, which we don't tend to actually deal with most of the time. We tend to break it up into pieces in most engineering design, unless you're dealing with full computer models, etc. Summation of forces in the z direction is equal to 0. Basically, our three equations of translational equilibria, and then our three equations, not forces but moments, and summation of forces about the y-axis equal to 0, and summation of moments about the z-axis is equal to 0. And so, again, we see that for the 2D case, we have 3 equations of equilibria, and for the 3D case, we have it's clearly demonstrated that we have a full 6 equations of equilibrium. Okay, so that is the basis of rigid body equilibria for both 2D and 3D systems. If we're dealing with more complex systems, well, again, how we actually apply this to the more complex systems, where we actually have systems with numbers, forces with numbers and angles and things like that, we'll explore those in later videos when we actually look at applying these. But this is actually the very basis, the very basics, and the very basis of, or the very foundation of rigid body equilibria for both 2D and 3D systems. I initially mentioned that I would include a discussion of the rigid body assumption in this particular part of the lecture, but I think I'm going to include that in a part 2, a very short part 2 of this lecture. So I think that would make a very nice discrete video. So, all right, I think that'll do it for part 1 of this lecture. That just covers a brief introduction to what rigid body equilibrium really entails, in terms of the equations of equilibrium. And I will see you all shortly for part 2 and part 3 and 4. Well, part 3, maybe part 3 and 4. Definitely part 2, definitely part 3, maybe part 4, as we go through this lecture, as we're discussing some of the theory and examples of rigid body equilibria. All right, that'll do for now. I'll see you all shortly for part 2 and probably part 3 for 3 and 4 and maybe even 5. And I'll see you all shortly. And as always, thank you.